6.2, still looking for volume, meaning we're taking a curve or a graph, we're spinning that thing around an axis, and then we're finding the volume of that solid, that three-dimensional solid. But now we're using another method, not the disk method or the, whoops, I didn't get my camera on. Not the disk method and not the washer method, but a brand new method, which is called cylindrical shells. Often they just call it the shell method, which is I'm not for certain why they use the word shell. The cylindrical method, maybe because that word's harder to write. Cylindrical. Okay, I hear you snickering over there. All right, section 6.2. Here we go. Volume by cylindrical shells. Cylindrical shells. That looks like a good word for a spelling bee, doesn't it? Cylindrical shells. Okay, so a little bit of processing. Okay, just kind of getting a little bit going on here. First, what in the world is a cylindrical shell? A cylindrical shell. Well, really a cylindrical shell is a cylinder, and it's going to be hollow, okay? So it's going to be a hollow cylinder. If you can kind of visualize a piece of PVC pipe, if it has a really thin shell, or if it's a really, the pipe is very big around, it's got a really thin white outer, what would you call it, substance, okay, then that would be what we're talking about here. So this looks kind of like a roll of toilet paper. It's not my goal. But this is your cylinder, and if you make it so that it's really got a big hole and it's got a tiny little rim, then that is your cylinder. Okay, that is your cylinder. The goal when we integrate is to make the thickness of this cylinder, something like a piece of PVC pipe, to make the thickness as small as possible. And in other words, extremely small. Or in other words, that thickness is our dx under integration, which is going to 0, or our delta x when we use summation, which we want to approach a value of 0 to get great accuracy. So if we want to know the area or the volume that this cylinder holds, think about this. If I cut this and open it up, okay, if you cut this, if it's hollow, there's no top or bottom, and you slice it down the side and you open it up, it's going to be a rectangle, right? It's going to be a rectangle if you do that. And so then, if you recognize that the top of this was the original circumference of the cylinder, then the top is 2 pi r, circumference of a circle. So when you open up that circle or that cylinder, that top of that rectangle would be the circumference, which is 2 pi r. So if you look about the area, we always call this 2 pi r times h, because this height here, we use h. Pretty straightforward, the height is h. So instead of really saying length times width, we're saying circumference times height in order to get the surface area. Well, that's the surface area. Now if we take it into 3 dimensions, okay, if we throw this into 3 dimensions, then this thickness amount, that thickness is really the width of the substance that the PVC pipe is made out of, that you want to be paper thin, because you want the width to be approaching 0. And so when we go into volume, we have 2 pi r h times that thickness. I don't know, call it x. But then when we integrate, we're going to add all these volumes together, a whole bunch of them, infinitely many of them, because the thickness is approaching 0. So when we find volume by integration, we integrate the area, which is 2 pi r times h, times the thickness, but the thickness is dx, because dx is approaching 0. The thickness is approaching 0. So when we find the volume of a solid, which is created by spinning a curve around an axis, we're going to integrate or take the sum of numerous of these little cylindrical shells in order to find the volume. So that's kind of the process of what's going on. You're breaking all this mess into cylindrical shells and adding them together to become the volume. Now, when we work in this, it depends on whether you're working in X or Y. If you have a dx, your R has to be in the X variable and your H has to be in the X variable. So if you're doing a dx kind of integration, play with the X variables. If you end up doing dy, you're going to be playing in the dy variable. So always stay with the Y variable if you're in dy and the X variable if you're in dx. So now I'm going to pull the textbook up and show you some figures of how these lovely cylinders are being used. These infinite number of cylinders are being used to find the area under a curve. And in our textbook, I'm going to look under page 400. Oh, that's not right. Different book. Which book do I want to use today? Oh, I can use this book. Page 320. So I'm going to look at page 320 just to kind of give you a vision of how these cylinders are helping us to find the volume of this solid. Okay, so here it is. Here at the bottom of this page, you see our cylinders. They do a really good job of showing you how if you cut it and open it up, it turns into this rectangle. Okay, and then how you come up with the volume of this. So this is kind of a vision of what I just showed you about taking something like a PVC pipe where that little width, that thickness of it needs to be extremely small, and opening it up into this version in order to come up with volume. So then, how does that work under a curve? If you have a curve that's being spun, this curve is that blue parabola that's concave down. Okay, actually, let me shove her in. Here is your parabola that's concave down. It's spinning around the y-axis. No, it's not. It's spinning around that red line. Okay, it's spinning around. And when you spin it around, it comes up with this strange-looking shape here. Well, now what we're doing is you can see the cylinder underneath here that's used to try to find the volume of that object. And you're going to have multiples. This is like concentric cylinders, one inside the other, over and over again. And your cylinders are short as you get inside the middle, and then the cylinders will get taller as you go up to the peak, and the cylinders get smaller. So the cylinders are coming from here. They get bigger radii, bigger radii, bigger radii, okay? And then it gets tall, and then it gets short. So you're having multiple cylinders underneath that curve, and we're going to add the volume of all those multiple cylinders to come up with the volume of that entire object from spinning it around. So here's another similar vision. I'm sliding the book over a little bit. Here's another similar vision. Here's kind of the two-dimensional vision of it, or a slice of it, where this is the wall of our PVC pipe that when you spin it will create this cylinder. Okay, so this is like a slice of the cylinder. When it spins, this is what it looks like, but this is the slice of it. So kind of getting a vision. And again, you can see the book really, and all textbooks push what's called the shell method, but really it's cylinders, cylindrical shells that we're using to come up with the volume underneath the curve. So there's some pictures of it all. Hopefully that'll help you out a little bit. So now when we integrate, if you integrate with respect to dx as above, and you're integrating 2 pi r h, 2 pi r times h being really the area of a rectangle, times the thickness here, the thickness is going to give you the volume. When we do this, the r is going to be the radius of the cylinder. Okay, this is the radius of the cylinder from the axis of revolution. Okay, from the axis of revolution. The other thing about the radius is the radius will equal x if you're rotating around the y-axis. Most cases. Normally, often x, okay, make that a little squiggly, often x, if rotating or spinning about the y-axis. The dx is the thickness of the wall, the thickness of, well, let's call it the cylinder. The thickness of the cylinder, okay, the thickness of the piece of plastic that's making the PVC pipe. The h is the height of the cylinder. The height of the cylinder. And normally the h is going to be your function value, the name of the curve. Usually your h is the name of the curve, and so I'm going to put f of x here. It might be a subtraction of two curves, like an f of x1 or an f of x minus a g of x, but usually you're going to play with the function value when you're using the height. All right. Let me see if I got something else I can show you real quickly. It's usually actually a distance x, usually the value x. Yeah. Yeah. Well, I don't know where I'm coming up with these page numbers. Okay. So here we go. Let's give this a shot. Okay, so let's jump in and do some examples of rotating about a vertical axis, and then we'll come back and we'll rotate about a horizontal axis. Rotating about a vertical axis is easier in this case, so we're going to do some examples. Rotating about a vertical axis. All right, so I'm going to go to the textbook, actually, and I'm pulling this from the textbook so we can have a relatively good picture to show you. And then I'll draw a picture, and it's not going to be so bad. Okay. Oh, and I was how I can have my page numbers so messed up. Okay, I'll figure this out. Where did this one? This says example 2 on page 412. That can't be right. Let me see which book this was. Must not have been any of these books. I don't know where I'm coming up with all these page numbers where I get them so messed up. X square root of x about x equaling 4. Okay, example 2, page 322. Okay, here's the question. Find the region bounded by the curve y equaling the square root of x, comma, the x-axis and the line x equaling 4. Now, revolve this about the y-axis. Okay, revolve this region about the y-axis to generate a solid. Determine the volume of the solid. Using the cylindrical shell method. Okay, so let's get an idea of what this graph looks like. We know what the square root of x looks like, and I'm not going to get fancy with these graphs, but the square root of x looks something like that. There's your square root of x. Now, you're going to have your curve is bounded, y equaling square root of x, the x-axis, and the line x equaling 4. So let this be the line x equaling 4. So you have this region bounded by the x-axis, the curve, and the line x equaling 4. We're going to rotate this thing around the y-axis. So you start spinning it. It's going to look something like that when you start spinning it to get a vision of what's going on here. So you're looking, if you're going to try to get a picture here, kind of get a little circle here in your mind. It's going to be hollowed out, kind of like a funnel on the inside. Now, we're going to use, if we're rotating about a vertical axis, we're going to be integrating with respect to dx, just the opposite of the last section. When you're rotating about a vertical axis, you're going to be integrating with respect to dx, which means these up and lower limits of your integration must be x values. And so I'm going to go ahead and put x's on there to remind you, if you're integrating with respect to dx, your upper and lower limits must be x values. Then this is going to be 2 pi r h. Now we've got to figure out what r is and h is and all those little x's are. Okay, so now your upper and lower boundaries, your upper and lower limits are going to go from the origin to this point where your vertical axis or your x equaling 4 line is. So your upper and lower limits are actually easily 0 to 4. So you're integrating from 0 to 4, 2 pi r h dx. Now, visualize having yourself a cylinder with a tiny little width here, and this cylinder is what's spinning. These two little vertical squares are creating a cylinder that's spinning around this circular motion around that y-axis. So if you visualize this cylinder, then what you're looking for is the radius from the axis you're spinning from. This is your radius, and this is your height. Now, the point right here on the curve, its ordered pair is xy, but we want everything in the variable x, and so we're going to rewrite this ordered pair as x square root of x. So therefore, when you're integrating from 0 to 4 of 2 pi, your radius is the horizontal value of that ordered pair. Your radius is x, and your height is going to be f of x. I'm going to go ahead and put on here f of x. So you're simply integrating from 0 to 4, 2 pi x, and the height is square root of x dx. And your integral is set up. So that is, the integral is summing up the volumes of infinitely many cylindrical shells underneath that curve as it's spinning around the y-axis. This would be like length times width times thickness to give you volume. And so this integration is not difficult. Of course, you would go ahead and say 2 pi x times x to the 1/2 is x to the 3/2 dx. And when you integrate this, you're supposed to end up with 128 pi over 5. Okay, not bad, right? I need to give y'all a minute more.
Is that like units cubed?
Yes, I should put that on here. And you know they don't put this anywhere, anywhere in my math lab, anywhere in my test generator, anywhere in this textbook. You know, I don't see that anywhere, but it is volume. Now, here in your textbook, I'm going to show you a picture. You see my picture, two-dimensional. Here's the picture on page 322 of the textbook. Still not exactly, really, they're still not three-dimensional, but here's our curve. Whoops. Here's our curve. Here's kind of the vision of one of the shells, one of the cylindrical shells, and there's a bunch of them, concentric ones, all underneath that curve. Okay, so that's a pretty good image. Visualizing that's one of them, but there's many, many, many of them. They're creating, and their heights are varying as it moves along the curve, which is all being taken into place within that integral. Pretty nifty stuff. Okay, so let's try another one. Okay, I'm pulling this one from another textbook. It's from my Stewart textbook, and it says, find the volume of the solid obtained by rotating about the y-axis. So we're sticking with the y-axis. Okay. Find the volume of the solid obtained by rotating about the y-axis, the region bounded by, and we have the curve y equaling 2x squared minus x cubed, and y equaling 0. Y equaling 0 is the x-axis. So what does this look like? You could graph on your calculator if you want to, y equaling 2x squared minus x cubed. It's going to look something like this when you do. And then it says y equaling 0. Y equaling 0 is the x-axis. You guys know that. This is the name of the x-axis in equation form. You're spinning this thing around the y-axis. So you're doing this. Yeah, it does look kind of like little skateboard ramps. Okay, that's what it's going to look like when it starts spinning. A little bit better than that. Okay, if you're integrating around a vertical axis, you're going to integrate 2 pi r h. If it's around a vertical axis, this will be dx. And these are going to have to be x values. Your upper and lower limits are going to have to be x values. So your x values are going to run from 0 to whatever this point is over here on the right of this curve. So in other words, this curve, we need to know the x-intercepts. So to find the x-intercepts, which is going to give me my upper and lower limits, I take the 2x squared minus x cubed and equal it to a y value of 0, which factors into an x squared minus, or an x squared times a 2 minus x, which means that x squared equals 0, or x equals 0, and x equals 2. Well, one of them we already show right here at the origin. This over here is a value of 2. So you're going to be integrating now from 0 to 2, 2 pi r, which r is going to convert into x, and h is going to convert into f of x, dx. And I usually put approximately, because this isn't it. We're getting to the full integral, and trying to get the integrand right and everything. Now, we're looking at cylinders being used, cylinders underneath the curve. So really, if we put a cylinder underneath here, really thin, narrow cylinder, then this point where it touches the curve is a point xy. But it is the point x, 2x squared minus x cubed if we're going to play in only the x variable, because we're integrating with respect to dx. Remember, dx is the width of that little rectangle I put in there, which is supposed to be approaching 0. This region is my radius. Okay, that's my radius. My radius is the horizontal value from the axis that we're spinning around to the point on the curve, which is going to vary as the cylinder moves on the curve. But that will be x of our ordered pair. So the radius is replaced by x. The height of the cylinder is right here. This is your height. What is your height of your cylinder according to that ordered pair? There you go. It's 2x squared minus x cubed. So now my integration becomes integrate from 0 to 2 of 2 pi x. F of x is 2x minus x cubed dx. And now you're ready to actually just do the algebra and the mechanics of integration in order to come up with the volume underneath that solid that's created by rotating that curve around the y-axis. Now when you do this, I'd pull the constant 2 pi out front. Then I would distribute that x, giving you a 2x squared minus x to the 4th dx. And that will not be too difficult to integrate. It'll integrate pretty easily. And I'm showing that the answer to this after you integrate is 16 over 5 pi cubic units. Let me see if I can show you a picture of this one now. Sometimes it's easier to just go ahead and set it up and do it, then later look at the picture and see if it all really fit together. Here's a little bit of a vision of it. Right here. Here's the curve. There's one of the cylinders. There's a bunch of them, but there's one of the cylinders. And if you spun it and stepped back and looked at it kind of from a top view, this is what it would look like. Okay. What's really interesting in this diagram is it kind of shows this curve as it's spinning to try to help you to see that view from the top of that object. Okay. What are y'all laughing about? You're having more fun than me. Trying so hard to teach this well to you. Trying to make this easy as possible. Okay, here's another one. Y'all seem to be taking this no problem. I'm just teaching it very well. How's that? Okay, find the volume of the solid. This is still from Stewart. I pulled this from the Stewart book. Obtained by rotating. He writes his questions all the same. By rotating about the y-axis. We're still going around the y-axis. The region between y equaling x and y equaling x squared. Okay, so find the volume of the solid obtained by rotating about the y-axis, the region between y equaling x and y equaling x squared. So, of course, we need to get a graphical view of this, try to figure out what in the world this thing looks like. Okay, and like I said, no fancy graphs. Okay, y equaling x is just going to be our perfect 45-degree line. And y equaling x squared is our parabola whose concave up, whose vertex, of course, is at the origin. So that's what the region is going to look like. We're going to spin it around the y-axis. So when we spin it, it's going to look something like that. So here's your spin vision. Okay, so anytime we're using the cylindrical shell method, we're rotating it around a vertical axis, it's going to be in respect to dx. So we're kind of looking at this 2 pi r f of x dx kind of set up moving with your upper and lower limits of x1 to x2, or just x values. We can see that our lower limit's going to be 0, our upper limit's somewhere over here. So to find the upper limit, it's going to be the point of intersection of these two graphs. The lower limit's 0. We both know that both of these graphs are going through the origin. So how to find the upper limit is to find the point of intersection of y equaling x and y equaling x squared. This is going to give me that point of intersection. So I set these two equal to each other. So 0 would equal x squared minus x, factored into x times x minus 1. So sure enough, one of the x values is 0, which we could tell that by the graph, and the other is an x value of 1. So this is a 1. It's intersecting over here at 1. So our upper and lower limits for our integral are going to be from 0 to 1, this 2 pi r, and r is probably going to end up being x, f of x dx. Okay, slowly but surely we're coming up with this integral. Okay, so now let's get a vision of this cylinder, or one of the infinitely many cylinders that are spinning. Here is the cylinder right here. Careful, the cylinder didn't go all the way down to the x-axis. The cylinder is between the two curves, right? The cylinder did not make it down to the x-axis. It's a little bit above the x-axis here. Okay, r, the radius of this circle, is going to still be this distance here, which is just x. So our radius, because remember this thing is sliding between these curves, and so it'll always be the value of x as it's sliding. Okay, so if you want to look at these ordered pairs, this is the ordered paired x, y, which is just going to be x, x on the linear graph. So the radius is still going to be x. So your radius is x. Now, what in the world is your height going to be? This is the height. There you go. Okay, where in the world is he getting x minus x squared? Okay, think about this. This point on the parabola, whose ordered pair is xy, is also xx squared. So that distance, because it did not go all the way down to the x-axis, that distance is the top minus the bottom, which is the y minus the y, which is really x minus x squared. So it's x minus x squared. I didn't have to put that in parentheses, but I did. Okay, top minus the bottom, your vertical height, okay, h, is the difference of really those two functions. So your integral finally becomes integrate from 0 to 1, 2 pi, r is the x, r is x, and f of x is x minus x squared, because the height of the cylinder is not going all the way down to the x-axis, dx. Now you're ready to go. You'll pull the 2 pi out front when you integrate this thing. You'll then distribute the x and get x squared minus x cubed dx. When you integrate this, this is supposed to end up to equal pi 6 cubic units. Okay, now I'm going to ask you, because this is rolling pretty smoothly, why is this dx instead of dy? We're rotating around the y-axis, but why is this a dx integration? Almost. What is dx representing? Dx, remember, is what? The thickness of the cylinder, right? This is the thickness of the cylinder. And here's your cylinder right here, right? So isn't the thickness of the cylinder an x amount? A horizontal amount? It's an x amount. That's approaching 0. It's supposed to be paper thin, smaller than paper thin, okay? But that thickness is a horizontal amount, which is a dx amount. Okay? Also, you're right. Your radius is a horizontal amount, which should be in the variable x. I missed that. What did you say?
It's a cylindrical Riemann sum.
That's correct. It's a Riemann sum of the volume of a bunch of cylinders. All right, so we'll do another one of these. Again, I'm going to keep doing these till y'all feel good and confident because the really bad part about your My Math Lab homework, really in all textbooks, is they're just going to give you an answer. They're not going to show you how to set up the integral. Okay, so here's another one. This is coming from Stewart too. It says find the volume. Thomas, our textbook, did 3 examples in this entire section. Yes, okay. All right, so we needed a lot more than that. Find the volume, which is not uncommon. I think every one of these books only had 3 examples. Find the volume of the solid obtained by rotating the region bounded by y equaling x minus x squared and y equaling 0, rotated about, and they don't ever write the word rotate again, but when you see the word about, that's where you're rotating. Rotate about, this is the word you'll see consistently, rotate about the line x equaling 2. Okay, so when you see the word about, they're giving you the axis of rotation. Okay, so again, this is a vertical line. So it's a vertical line as your axis of rotation. So we're still dx. Okay, we're still a dx thing, but we've shifted off the y-axis. So this is going to change our integrand, okay? It's going to look a little different this time. It's going to be a little bit more difficult, but I still think it'll be okay to look at it and understand what's going on. Okay, so we know the minute we're rotating around a vertical line, this is a dx thing. This is 2 pi r h dx, right from the beginning. So now let's take a look and see what this is. Okay, when you graph this, and you can graph this on your calculators quite easily, okay, when you graph it, it's going to look something like this. It's going to be like this. Okay, it's a parabola that's concave down. Then you're going to be rotating it around the line, the vertical line, x equaling 2, which is going to be over here. That's what you're going to spin it around. So you start spinning it. Okay, you start spinning it. Well, I didn't do that very good, but something like that. Now that one does look like a donut. Okay. Okay, that one is going to look like a donut. Okay, so now our upper and lower limits on our integral are x values. This one's going at the origin. This one we have to determine. So if I want to know the x intercepts, which are going to give me my upper and lower limits, then I need to go to this graph, x minus x squared, set it equal to 0, which means replace the y with the number 0 and come up with those intercepts. So then if I factor an x out, sure enough, one of those x intercepts was where x was 0, which was at the origin, and the other is where x is 1. So this is a 1. So I'm going to be integrating from 0 to 1 this 2 pi r h dx stuff. Usually r is going to be replaced with x, and f of x is going to be replaced with the curve, the equation of the curve. But we'll take a look at this graph and see how it's going to work for us. Okay. All right. So here is going to be our little rectangle, or the kind of like the cylinder. So we got to look at the radius. This is the radius right here. This ordered pair on this curve, xy, is also x minus x squared. And we don't want anything in y because we're integrating with respect to dx. So what is that length of that little r, that little horizontal line with the r next to it? There you go. Yeah, that's right. It is x, okay? The long region, okay, all the way across is 2. Subtract this region, the whole minus the part. the whole is 2, and the part is the x value of the point along the curve. The whole is 2, and the part is the x. So the radius is 2 minus x. So when you come off of rotating around the y-axis, your radius is going to, your radius value is going to differ. Now we got to talk about the height of our cylinder. Okay, the height of the cylinder is what? There you go. It's the y value of the point on the curve, which is just x minus x squared. So this becomes integration from 0 to 1 of 2 pi. Your r is 2 minus x, and your height is x minus x squared dx. Now, when you start rotating two curves, and you have an f of x minus a g of x in addition to the r changing, that's where it gets kind of interesting. Okay. All right, so now this becomes, you can pull the 2 pi out front, and when you do FOIL to the binomial times the binomial, this is a 2x minus x squared minus 2x squared is minus 3x squared plus x cubed dx. It's not a difficult one to integrate, and this is going to equal, somehow, it's going to end up equaling pi halves cubic units. That one will look like a donut when it spins. And it's not got a very good image in here. Okay, so now we've been rotating around a vertical axis. Now let's start rotating around a horizontal axis. Okay, when you start rotating about a horizontal axis and you're doing this 2 pi r times height, this is now going to be dy. It's now going to be dy. So these values are going to be y values for your upper and lower limits. Those are going to have to be y values also when you're spinning around a horizontal axis. Okay, in general, this is now going to be an integral from a lower y value to an upper y value of 2 pi. R will often be replaced by y unless you come off of the x-axis. And your height will be f of y unless you have two functions in which it might be an f of y minus a g of y. So that's just kind of a general set it up. If you're rotating around the x-axis, that will be y. But if you come off of the x-axis and start rotating around another horizontal axis that's a little higher or lower, then the r will change. Okay. Also remember, the r is the radius of the cylinder. Not the radius of the cylinder. It's the radius of, how do I say that? The radius of, it would be, well, yeah, it is. Well, no, it's the radius of the cylinder, but not the thickness of the cylinder, so that's okay. The radius of the cylinder, it's okay, I can say that. The h is the height of the cylinder, and the dy is the thickness of the cylinder, which is supposed to be 0. Okay, it's supposed to, well, paper thin, approaching a thickness of 0. Okay, this is example 3 on page 323 of our Thomas book. And what it says is it says find the region bounded by the curve y equaling the square root of x, the x-axis, and the line x equaling 4. Revolve or rotate around the x-axis to generate a solid. Find the volume. The region bounded by the curve y equaling the square root of x, the x-axis, and the line x equaling 4. That's going to give us our region we're going to spin. Then take that region, revolve it around the x-axis, which is going to generate that three-dimensional solid, and then find the volume of that. The minute you start rotating around a horizontal axis, this is a dy integration. So you're thinking very quickly, 2 pi RH. I'm going to be going from a y1 to a y2. I'm integrating with respect to dy these cylinders. Now let's graph it and see what we really have here. Rotating the other way. So here's my square root of x. Here's my x equaling 4. And my x-axis. So it's the same thing as we did earlier, but now we're rotating it around the x-axis, making it look like this. It's going to take y'all a minute to see this one. Okay, you got to kind of shift. You're spinning it. Okay, you're spinning it. But your lovely little cylinder is right here. Let me find a place to put my cylinder. Here's a good place to put my cylinder. Right? Because when that cylinder is spinning, that's what's called, you see the cylinder spinning right here. Underneath there. Like a piece of PVC pipe. That's why it's dy, because the thickness of this cylinder is a vertical amount. The thickness of the cylinder is a vertical amount. That's why it's a dy. Okay? This point on this curve is going to be an x, y. But if you're going to be integrating with respect to y, everything needs to say y. So in other words, if y equals the square root of x, then y squared equals x. So this ordered pair is y squared y, because you need to get everything in the y variable. If you're integrating with respect to dy, you must get everything in the y variable, and so x equals y squared. Now, you're not integrating from 0 to 4. You're integrating with respect to an upper and lower limit, which are y values. So your integral bounds are 0 to whatever this is up here. Okay, you're integrating y. You're sliding up and down. This cylinder is sliding up and down. So this point here, I need to know the height. Well, if x is 4, what will y be? It'll be 2, because it's the square root of x, or the square root of 4, which is 2. So this is a height of 2. So your upper and lower limits are 0 to 2. 2 pi RH dy. This is what my volume, something like this. Okay, now then, what is my radius? My radius, look at where your radius is right here. There's your radius right there. Okay. There's your radius. This is R, which is this height at this ordered pair. This is R, which I keep putting it over here because it makes more sense, but this is R, which is this Y value. This Y value that I'm circling is the radius from the point of the axis of rotation to my cylinder. That distance is Y. So my radius is Y. My height of my cylinder is right here. This is my height of my cylinder. So my height of my cylinder is going from this point to this point, here to here. This is a point 4y. X is always 4, because that's the vertical line, x equaling 4, and the y is whatever the y is there. So what is the distance between these 2 points? This is interesting. There you go. It's 4 minus y squared, right? 4 minus y squared. This is a 4, and this x, this horizontal value is y squared. Right? This horizontal value is a y squared. An x, but you can't have x, y squared. You cannot have x, it's y squared. So now this volume is integrating from 0 to 2 of 2 pi. R is replaced by y, and your height is replaced by 4 minus y squared dy. Now you're ready to go. It's a little different, isn't it? The whole perspective is throw everything into the y variable, which feels a little odd. So when you get ready to just do the mechanics of integration, pull the 2 pi out front and distribute the y. Integrating from 0 to 2. And this is supposed to then equal 8 pi. Okay, let's try another one. We might actually get out a little bit early today. I'm afraid for y'all to take a break just yet. Okay. Don't want y'all to break this focus right now. Okay. Find the volume of the solid of revolution formed by revolving the region bounded by the graphs of y equaling x cubed, y equaling 0, and x equaling 2 about the x-axis. Okay, so we're rotating about the x-axis, we're rotating about a horizontal axis. So when you see that horizontal axis, this is an integral with respect to dy. These are cylinders, so I'm supposed to be doing this 2 pi r h thing. dy. These are going to be y values for my upper and lower limits on my integrand. Okay, so let's get a vision of what this thing looks like. Y equaling x cubed. X cubed, starts down here and then it levels off and then it goes back up. So it almost looks like a parabola, but it's not. Okay, it looks like something like this. Y equaling 0 is the x-axis. And x equaling 2, I'll just put it right here. Okay, we're coming around the x-axis, so it looks like this. And here's my little cylinder. My cylinder must stay inside my shaded region, so it doesn't make it over to the y-axis. It stays inside my shaded region. This thing is spinning. You're just looking at that tiny little piece of rectangle spinning. It's hollow. It's very hollow. Okay, so if my upper and lower bounds or upper and lower limits on my integral are vertical, they'll be from the origin up to here, whatever these are, 0 to something up here. So I really need to know this ordered pair on the curve to get that height. So I know this is an x value of 2 and a y value of 8. Okay, so I know that I'm going from 0 to 8 of this 2 pi r h dy business. Remember, my r is usually replaced by y. This is your r right here. We don't know how high it is, right? It's moving. But if you want to look at this ordered pair, this is an ordered pair x, y, but everything must be in y. So what is x here? If y equals x cubed, you take the cube root of each side to get x. So this is the cube root of y, y. So the radius is this height, or the distance this cylinder is from the axis of rotation, so it's just y. And that'll hold pretty true whenever you're rotating around one of the axes, the standard x or y axis. Now, this is the height of the cylinder. Okay, the height of the cylinder. Now, this point here is where x is 2, and we don't know what y is. So what is the height of the cylinder? Okay, you got the cube root of y, right? The cube root of y is the first ordinate in the ordered pair, right? So what's it over here going to be? 2. 2 minus the cube root of y. Okay, so it's 2 minus the cube root of y. So you're integrating from 0 to 8. 2 pi, replace the r with y. And your height, and I should have put f of y here because that's what we're going to do. Height is usually f of y, and r is often y. So this becomes, the height though becomes 2 minus the cube root of y, all dy. So when you actually do this, okay, pull the 2 pi out front because it's a constant. And then this will say 2y minus y times the cube root of y is y times y to the 1/3, which is y to the what? 4/3. That's a 4/3. And when you do all this lovely integration, this is going to be 128 pi over 7. Okay, one more, but this next one's, I even have written in my notes, wow, okay. Okay. This next one's kind of fun. Here we go. Find the volume come on. Find the volume using cylindrical shells. Okay, I'm giving you all versions of the way the question can be asked, okay? They're all asking the same kind of question, but the wording is a little bit different. And they have your curve is y equaling the square root of x minus 1, y equaling 0, x equaling 5, and they say about y equaling 3, which means rotate about the horizontal axis y equaling 3. So we've come off the x-axis. We're still rotating around a horizontal axis, but it's not the x-axis anymore. So this is still a horizontal axis of rotation. Which means we're still, when we're using the cylindrical shell method, it's still going to be a dy. So we're integrating with respect to dy because we're rotating around a horizontal axis. So this is going to have to be 2 pi r f of y, whoops, that's height, 2 pi r h dy, with y values as our upper and lower limits. Let me change that. Let me get rid of this, scratch it. 2 pi r h dy, which will end up becoming something along the lines of 2 pi y. Might have to shift the y around a little bit, so I'm going to put approximately, and my h is going to be approximately an f of y dy, just to try to get yourself founded. Okay, your r is usually somewhere with y. It might be a y plus 2 or something if I'm not rotating, perfectly around one of the x or y axes. And my f of y might be the difference of two functions, something, but it's a function value. Okay, so let's take a look at this region that's spinning around. Okay, y equaling the square root of x minus 1 is the square root of x shifted 1 unit to the right. Like that. I probably drew that too big. Maybe not. Okay, then we have x equaling 5. So here's my x equaling 5. So this is a 1 and this is a 5. I'm not doing it, I'm just kind of, I'm off a little bit if you really want to look at the tick marks on here. And y equaling 0 is the x-axis. So here's your region. Remember that y equaling 0 is your x-axis. Spin this thing around y equaling 3. Spin it around y equaling 3. No, let's say that y equal 3 is right here. There we go. So this is the spin. Looks something like that. Something like that. Spinning. Okay, so here, let me put a little cylinder in here. There's my cylinder that's spinning around. So here would be the other part of it up here. And here it is spinning. Doesn't look so good this time. Kind of like that. It doesn't look as good. Okay, so my boundaries. This is a height of 0, and this is a height of what? So your lower limit is 0, and your upper limit, he says it's 2. Well, let's see. This point right here is where the x value is 5. So if the x value is 5, 5 minus 1 is 4. So you have the square root of 4, so it's a 2. There you go. So you're going to integrate from 0 to 2. How did I do that? Y equals the square root of x minus 1, and since x was 5, I need to write that down for you for your notes, your reference, so y is 2. Okay, your radius. Here's your radius from here to my rectangle. Well, we got to think about this one now. This is your radius right here. What is the length of that radius?
3 minus y squared.
Okay, this point right here would be 5y. Right? And this is a y value of 3. So what did y'all say? 3 minus y, right? Think about that a minute. Those are vertical values, so that's the second number in the ordered pair. It's the second number in the ordered pair, so it's got to be the y. It's height values. Top minus bottom, a height of 3 minus a height of y. So your radius is 3 minus y. Okay, now what is this, which is really the height of my cylinder? Well, we need to get a value here. This is what? This is xy, but everybody's got to be in y. Oh, boy.
That's 5 minus y squared.
Let me get my screen back on. If I have to solve this guy for x, I'd square both sides. Y squared is x minus 1. So y squared plus 1 is x, right? So this is the point y squared plus 1 y. That's a y squared plus 1 y. So this distance is a horizontal, a big horizontal, minus a little horizontal. The big horizontal is what? What did y'all come up with here? Almost. It's 5 minus what? There you go. Which is not a 6, but a 4 minus a y squared. Okay, so this comes down through all my mess, okay? So you're integrating from 0 to 2 of 2 pi. Your y, which is your radius, is replaced by 3 minus y. Your height is replaced by 4 minus y squared. That's a pretty tough one. So you're integrating from 0 to 2. I'd bring the 2 pi out front and then do FOIL with these two binomials. So this is what? 12 minus 4y minus 3y squared plus y cubed dy. And wave the magical wand. Somebody's doing a lot of work. It goes 24 pi cubic units. Because it is a volume amount. That's a pretty tough one, people. Right? That's an interesting one. You should be really full of intelligence right now. In fact, you should feel a little bit overwhelmed. You slowly but surely have kind of dug a little deeper, a little deeper, a little deeper, and you followed me all the way through. Now what it means is when you go home, okay, you've gone home, you've watched a little TV, you've been out to eat, whatever y'all do, and you go home and think, okay, what were we doing? What was going on in calculus class? I can't quite remember. Okay. So don't wait too long before you choose to tackle your homework. Okay? So remember what's going on here. You're rotating. Remember, just a second. 6-1 was rotations involving disks and washers and integrating pi r squared stuff. Section 6.2 is cylinders. 2 pi r h, and the dy seems wrong. Yes, Mike?
Is there going to be any slicing on the test?
No, I'm not going to do the slicing thing. Okay? So y'all remember now. Have a good weekend.